Hello, everyone, and welcome to the chapter talkthroughs for From Social Science to Data Science by me, Bernie Hogan. This is Chapter 9, Visualizing Expectations. So in this chapter, we're going to look at visualizations, how we can make best use of some of the features of Python, how we can compare something that we see as a visualization to perhaps something that we would expect in a more statistical manner, and use kind of the dialogue between the two of them to understand why it's really useful to have both some familiarity or experience with statistics and statistical methods, but also some familiarity with ways of expressing data visually. Now, visualization is not just about making a graphic look attractive or aesthetically pleasing, although that's really important, but really within data science and within science broadly, the purpose of visualization is insight, not pictures. And the point is to be able to understand what insight you want to communicate from the specific object or thing that you're presenting to the audience. Now, in the case of data, most of what we're presenting would be distinctions and distributions. And so we'll see examples of both later on. But before that, let's have a sense of where we're going today and give an overview of the learning goals. So first thing we're going to do is produce a distribution using a random number generator. And that's going to be hopefully pretty boring because we're going to want a uniform distribution. We're going to want to have a look at what happens when we expect things with it. We're going to want to plot that distribution using matplotlib, and I'm going to use Seaborn as well in this. There's lots of visualization packages out there for Python, but Seaborn is particularly tidy and has some nice clear guides and tutorials. We're going to understand how a trend line, such as a regression line, can be calculated. And then we'll annotate a figure with interesting details based on expected values and confidence intervals. So we'll use statistical tests to compare two groups. We're going to use a t-test and ANOVA, and how to compare two distributions from the same group, and that will be, say, using something like a correlation or a regression. So these statistical tests can be very, very deep, and there's a lot of compelling work that you can do in terms of the mathematics of them. We're going to be just a wee bit mechanistic in our use of them today, but we'll also just see this as an invitation to become more acquainted with why a certain statistical routine, such as a t-test or a regression, is useful in making a claim or accounting for things in a distribution. Then, of course, it's really up to you to go a little deeper into these tests afterwards. Now, we're going to consider the elaboration model as well for multivariate work, and that's a conceptual device, really, as much as anything. And it's a way that we can try to think about how a third variable can help us understand the presence or absence of a relationship between two variables that we already have. Okay, admittedly, I'm playing a bit safe by starting with Anscombe's quartet. This is a pretty well-worn example, but it's really useful, and it's worth revisiting here. It also has some very tidy code within Seaborn in order to render this yourself. So Anscombe's quartet is a really excellent example of showing why a visualization can help guide us in some ways that maybe statistics might not reveal, at least directly. So what we have here is a distribution of numbers. We have 4 different distributions. And between their x and y values, if you look at things like the mean, the median, or the standard deviation, they're either exactly the same or they're really similar. But yet, if we look at them on an xy plot, we can see that there's real qualitative distinctions here. Up in the top one right here in dataset 1, this is just kind of a standard strong correlation, kind of moves around the trend line. And in dataset 2 right here, we have what's it's curve, a curve number. We would want to model that perhaps with a curve. Now this one right here, we'd want to inquire a little what's happening because it looks like we have a pretty straight association except for one outlier. And similarly in this one, another outlier right here. So whether that outlier represents a different class and an instance of something that's just qualitatively different, or if there's actually some unmeasured variation within there, that's a sampling matter and something that we would be a bit outside the scope of this, but it's important for us to know that this is there, and because it's there, it is distorting what can be seen as otherwise a pretty obvious or efficient relationship. So let's have a look there at all of these. I mean, we can see the mean is 9 for all of them. The count is 11. There's 11 dots. And the standard deviation is exactly the same as is the median for X. And for Y, it's pretty darn close as well for all of them. So from this, you wouldn't really get a sense of the shape in the same way as the visualization. So we can reproduce that. We could reproduce that code in Jupyter. Now, looking at the chapter here, it's worth pointing out that this has got a couple tweaks lately to make sure it's A-OK for Python or Pandas 2. But overall, it's pretty consistent from what it was before. So over here in the code, I've just cleared everything out. I'm going to save this. It's kind of an empty notebook there right now, and run the code. First, we're going to import these things here. Now, I want to point this one out. I've shown this a little before, but it's especially important here in the chapter on visualization. This is figure format SVG. This is a way of saving, or at least presenting figures in a vector format. Now, a vector format means if we zoom into this, it's still going to look clear because it's all based on geometry. Now, it's different than, for example, a raster format like a PNG. Now, PNG can be really crisp, but if you zoom in, at some point it's just going to get pixely. Saving your figures in a rasterized format is really useful if you are planning on doing scholarly work, publishing, because depending on the journal or the venue in which you publish it, a rasterized figure may end up being reproduced in a really poor manner. It could look really blurry in the text. Imagine if it's in like a paperback book, and these things can get very blurry. So we want to just stick that one in there to see them here, but you'll also want to export your graphics as well to something like SVG or even PDF, and PDF can often import into other documents really easily. So we have the Anscombe's quartet here. We're just going to load it. Now, don't worry about this warning right here. This is a new one, or a temporary one at the moment in matplotlib. It will, in the future, it'll probably just go right away. And so we have the quartets here. Now, in running this, one thing I wanted to point out here is this hue. And hue, means different color, but what it also means is this is a way of faceting the data set right here. So if we actually have a look at the data set below, we can see data set, and then there's 1, 2, 3, there's 11 in each of them. And so hue is data set right here, and so thus each one of them will be its own individual figure. And we'll see that faceting by hue again within Seaborn as we go along. If we're visualizing expectations, and in many ways we're really visualizing distributions and a sense of how those distributions may meet or not meet our expectations. So distributions help us understand the shape of a series of measurements, and then we can also just get an extent of how expected is an expected value. So for example, if we have a normal distribution, we have something where we have a very coherent expected value. It's right in the middle. There's just as many values on either side. And as you get further away from the expected value, the numbers become increasingly less common, less likely. So it gets more and more rare. And so that's why it gives it its nice bell shape. But, sometimes a distribution might be really janky and there's lots of like lumps and curves, or it might be like extremely steep. And those things can all help us understand a little bit about what we might expect from measurements of that in the population. So there's many visualization types, aesthetics, colors, all sorts of stuff. Over here I've pasted some of the examples from matplotlib. As you can see, they're describing different shapes or facets, adding different forms of bar charts or things together, as well as showing distributions in both planes as well as within lines. So visualizations here can help give us intuitions. Now we should then consider how to test those intuitions statistically. It can also help us explain something that might be overly abstract. You might be able to do something statistically, but by showing it on a graph, it can help understand the logic or the reasoning behind it, really communicate that quite effectively. So this is from the Matplotlib gallery, and you can go check that out there. So to start with some distributions in this chapter, ironic for something on data science, is that we're not really going to use any data here at first. Instead, we're going to use a random number generator. But there's a reason for that. And the reason is because a random number generator should give us a very consistent expected value. So here we have an example of just a random number generator, and the distribution is from low to high, size is 8,000. So really, there should be 8,000 divided by however many of these should be, it's 500. So there should be about 500 ones, 500 twos, 500 threes, 500 fours, and so forth. Now, is that really the case? Are we going to get exactly 500 for each of them? I mean, that would actually be pretty unlikely. So what we get when we run that is actually something where all the values are kind of near 500 right there. And the choice of a range of 16 and 8,000 here is not really particularly relevant. We could have went to 20 values, and then it would be like 8,000 divided by 20, and it should still be around some sort of, which would be 400. It would still be around that expected value there. But it turns out with these numbers, it kind of works out for some of the examples later on. So I want to point out something else here, and that is the seed. And the seed is a value that we can pass to Python so that when we use a random number, we always get the same series of random numbers. And that's because what we have within NumPy right here, which is the NP, is what's actually a pseudo random number generator. It generates numbers that are very, very close to what we think of as random, but in the limit, they're not random. There's some pattern to them, or there's still a little bit of information left. But nevertheless, they're really close to random and close enough to random for most work. And the bonus is that if you feed the same seed to that algorithm, you'll always get that distribution. So that means when you run this code on your computer, you should get a distribution that looks like this. But if you were to change the seed, the distribution should still be around 500, but it could be a bit high or a bit low and, all over the place. So really, there shouldn't be any trend within these numbers. So if we know how many values of 6 there are, it really shouldn't inform much of the rest of them. I guess at some point, once you get to here, and you know 14 of the numbers, you can pretty much guess the rest. But, the point is with these is that there shouldn't be any real correlation within the numbers. And there certainly shouldn't be any correlation with the sequence. We shouldn't get lower numbers more often and higher numbers less often. This line should really just always kind of hover around 500. So we're going to have a look at that now and look at that trend line. Okay, so if we go down here, we can see first, let's have a look at 3 different kinds of different distributions. And here we have a uniform one, a normal one, an exponential one. And you'll notice I didn't set the seed to these right here. So if I run this again, we'll get kind of just ever so slightly different versions every time. So here we are at the example that we had before. And so this is we're just going to create a uniform distribution. So I do that. That's my random number generator. And I generate some random numbers. And so the first way that I'm going to have a look at them is not to visualize it, but to use a table. I'm going to use value counts. So if we think of that distribution, we turn it into a series, then we can just do value counts on it and observe we have 507 zeros and 499 15s. And so here we have is our distribution. Now here we can plot that distribution, and you'll also notice what we do with Python, and this right here is a little bit of a mix of Seaborn and matplotlib, because Seaborn is a library that extends matplotlib as many visualization libraries do, and we'll see matplotlib again in a number of different chapters later on with the some time series stuff and with some networks. So here we have plt.subplots. Now what this means right here is that we're going to have a plot object. Now where did we get that? If we roll right up to the top there, we can see import matplotlib pyplot as plt. PLT right here, when you call it and you call these subplots, it creates this kind of empty canvas. And that empty canvas has this figure where you can fill things in, and then this axis. You will get used to over hopefully through a mental model of when to reference each of them, but it can be a bit tricky, and I've had to do a bit of trial and error on it myself. But it should be a little clear as we go on. What we notice here is that within any given figure, we can add things to it. So here we have a subplot for AX that's just within the figure. And then we can add a horizontal line. And then we do this plot in Seaborn, and it's still adding it to the axis. Then we're adding a legend, and then we show it. And so here we have the legend right here, and all this work. And there's other things that we could put in this figure, and we probably should, but we'll see those later. I just want to keep it simple and look at this right now. If we comment out this right here, you can see we just have the figure itself. You'll also notice that because the label isn't there, it doesn't show up in the legend. So now let's think about that uniform distribution as 16 different cells in a table. It's just one long row, and it's got 16 cells. What we expect with our expected value within those cells is that we should take all 8,000 of our marbles or whatever, and just evenly fill them into each of the buckets, all 16 buckets. And so if we have things that are above or below that expected value, that doesn't mean that it's not random, or it's not that there's any information to be learned from this. Rather, if we have a random distribution, we should expect a little bit of variation. So we can tell that with a chi-square value. Now, chi-square isn't going to tell us a kind of a direction in a trend, but it is going to tell us that if we have some even set of expectations across a bunch of categories or boxes or cells, then if we do we see values that exceed those expectations, or I guess go below those expectations in a sort of substantively interesting way, or in what we would say here is a statistically significant way. Now, in this case, we have some dots here, and our expected value is 500 again. And there's one here all the way up at 525, and one down here at, almost by 460. So is this right here, is it really random? And when we look at the chi-square value, we get a p-value here, and the p-value is 0.9, which is, for our purposes, as a way of saying almost as good as random. We could expect this if we randomized, if we did it again a whole bunch of times, 90 times out of 100, we could get something that's as extreme as this. We could see values around this line right there with a range like this. Now, on the other hand, let's look at this x-axis. It's changed right here. And what I've done, and you can see it in the code, is we borrowed, I believe we borrowed a few from the low value and gave it to the high value. So we took two values and we made them more extreme. And so now the range, the highest one is 578, and the lowest is 410. So with now this time around, the chi-squared value is P002. I'd say maybe 2 times out of 1,000, you would see a value like this if you had a random draw. Now, 2 times out of 1,000, is that possible? Sure. So it really depends on our tolerance for deviation from an expectation. Now, in the social sciences, we often use a p-value of 0.05. So a 1 in 20 chance that you would see something that random. But that's not really a great score. It's just a way in which we say there's really likely something that's outside of our expectations, or outside of what we would have expected if there was no association between these things, if it didn't matter which bucket that it went into. So we can have a brief look at this in Jupyter down here. So first you'll notice I'm importing SciPy, or the Scientific Python library. It's one of many libraries for calculating stats, but I like it because it provides both p-values as well as some of the other values that you see. So here we are. We're just going to do chi-squared on our work here, and it says, and that's this distribution up here. And the expected value is indeed 500, which is the mean, and the p-value is 0.9. Should highlight that there. Okay, so now see what I've done here. I've taken one of those values, I've added 90 to it, and another one I've subtracted 90. Now, when I do that, we see a really high value up here and a really low value down here. And so these will be considered outliers. The expected value is, as I printed here, literally, but it's still 500, and yet the p-value is 0.002, so it's really unlikely that we would see this. Okay, so now, in addition to having an outlier from our expectations, we can also have trends. And so here we might see that we don't really expect there to be a trend. We shouldn't have a bias towards the higher numbers. It should just be even. And so now I chose this particular distribution right here because I thought it was pretty interesting, because it shows what looks to be a pretty big difference in a trend line here. It really shows a trend line going down. But I want you to have a look at this gray shaded area, or this lightly blue shaded area in behind. That area is the confidence interval for how confident are we in this trend line. And as you can see, we're not super confident. And we'll talk through that now in a second. So in this case, what we've done here is, instead of what we'll see as a correlation, this is a regression. And so here's the regression code. Here we're going to build in a regression with our formulae. We're not going to cover regressions too much in this book, but normally it's a way of helping us to describe a trend line. Now, if we fit a regression right here, we can get some estimations. And what those estimations tell us is, how far away are these points from these lines? And when we add up all how far away those points are, do we have a line that's, like, say we were to take the this line here on the screen. If we take that line and pull it up, it's going to get further away from some of those dots. It'll get closer to some others, but further away. And then if we do it this way, it'll get closer to those and further away from the original ones. And so somewhere along the way, if you were to add up the lengths of all those lines, somewhere along the way, there's going to be a minimum point. And that minimum point, that's going to be our trend line. So because we have a trend line, it's because we've found a minimum point in that sort of like little distribution space, but not because it's any good. The thing is that we could put a trend line that goes up or a trend line that goes down within that gray shaded area. And so because we can put a trend line that would be up or down within that gray shaded area, we can't be certain that the line's really going down or really going up. And so we see this here when we, with our parameters in the model. So when x is 0, y is predicted to be 505. So, well, it's right over there. And when x is 0, 95% of the time, y is predicted to be between here and here. So it's really confident that y is going to be here 95% of the time. And then when x increases by 1 unit, but here's the interesting thing, y is predicted to increase by minus 0.08. So, it's going to, with each increase, we hop down, we're going to go down by 0.8. 95% of the time, it's predicted to increase by somewhere between minus 2.7 and 1.2. Oh, so it's predicted to increase, not because that's a negative number and that's a positive number. That means 95% of the time it could go up or down. And that doesn't really tell us much of anything. That says that this here, while it looks like a trend line, it's not really a significant one. So this, in a way, is kind of the opposite of Anscombe's quartet. Whereas in Anscombe's quartet, what we did there is we used visualizations to reveal a pattern that we didn't really get to see within numerical distributions. Now this time around, what the visualization does is it gives us a hunch or an insight. But on the other hand, when we drill into it, it seems that that might be spurious, because when we think of things like confidence intervals, there's just so much range there that, well, our line, even though it does go down in the most, when we minimize those points, it doesn't have to go down 95% of the time with values like this. Okay, so let's have a look at another distribution here. And this is one that has a similar sort of sentiment to it. And this is a data across or births across the year in the UK. So this was a simple table that I downloaded from the Office of National Statistics. It's easy to kind of parse and put together. And within this, we can see what looks kind of like a trend line over the course of the year. Now, the first thing we can think about is the fact that it can't possibly be a trend line over the year, because this is an average of many years. So what it really means is there's probably some place where it goes below and some place where it goes above. Now, that sort of periodicity is in a more complicated model that you can do with time series analysis. We don't cover that in here, but it is worth noting that if this line is not exactly straight, it means there's probably one part of the year where births are more common, and another part of the year where births are correspondingly less common. So that's kind of interesting in its own right as maybe an intuition. Is there a time? Why would that be? And then we can also see in this chart here, another interesting feature of it, are these dots right here. And the fact that there's a real, there seems to be a real bias against this specific time of the year, and we see over here as well. And what's accounting for that? So right now we've already got an intuition based on a shape. So like I said before, we have these with things like generators, we get a very idealized distribution. But now in this case, a real life distribution, things are a little more up and down, they're a little more janky, and we then get to think, are these expectations of merit? Are they real trends, or are they just noise in the data? So here we have a regression. What we see here is that it does appear to be significant, and it explains a little tiny bit of the variation. It would say that we could say that there's roughly about 6% variation in the likelihood of a birth occurring by which day of the year it is. But that's not really that helpful for us. So let's see how we can enliven this chart to tell a story about this with data and with our ability to look at the chart and kind of put the chart and the regression together. So here we are in 4.1, testing uniform distribution, and we're just going to read in the data. If you've pulled down the files from GitHub, this should work just fine for you. And let's have a look at that, what it is. And so what we see here is we have very conveniently the indexes 0, 1, 2, and so forth. So that'll be able to align for the days. And you see here the average number of births, and this was over, I believe, a 20-year period, but I have to go back and check the data. And that would be 1,800 odd births a year on this date or this date and so forth. Okay, so here's what the chart looked like when we saw that. And it's called a reg plot in Seaborn, because what it's doing is it's doing a regression, and then it's placing that regression over the scatter plot, and it's also giving these confidence intervals, which come from the regression. So the confidence intervals are pretty tight, and what's kind of important here when we zoom in, and as you can see, because I did SVG as I zoom in, it doesn't really get blurry. That point goes above our expected value, and on the other side over here, it goes below on our expected value. So for that reason, it's unsurprising that it is considered statistically significant when we saw that regression. But what else can we do about it? What else can we think here? And so here's the regression. Now, I just want to briefly introduce this package. It's called Stargazer. And if you don't have it, pip install Stargazer. Now, what it does is it takes the values of a regression and various different kinds of regressions in Python. It's really quite smart about that, and formats it into a table, much like you'd see in a journal, rather than as a very large series of output or just very, very Spartan output that is hard to read. And so I like using that even while working on stuff. And here's what it looks like as a data frame. What we saw in the PDF is what happens when you render it as LaTeX. Okay, so now we have some features here, but let's go a little further and annotate that. Now, this is the most involved, I think, example of visualization you'll see in this chapter. So it's useful for me to just go through it a little bit in detail. Now here I'm going to preview what this figure is going to look like right here. And as we can see here, we have some axis labels. And so what you'll see here is we set number of births per year, days per year. And then we have some nice months down here. On the previous figure, which I can To recall up here, we just got days. We might say day of the year, which I guess is, technically true, but it's not especially enlivening. So if we have this mdates month locator, then we can sort of have our months over the year, and that's really useful. We have a legend down here, and we see here a 95% range. And I've also put a line in here. So this is December 25th, right here. And this is 9 months after December 25th. So what we see here actually is there's a spike in births kind of around 9 months after the Christmas holidays. Although during the Christmas holidays, there is a real set of outliers in terms of births. So what we see here are some different factors of the year or of culture in the UK, perhaps, that will intervene to some extent in this particular distribution. We have here a confidence interval for a trend line as well. And finally, I want to say I have occlusion-aware glyphs. Now, why do I have those? And that's because if you have a lot of points on a scatter plot, sometimes those points can overlap on top of each other. And where they overlap, if you don't, say, use transparencies or other features, you can't really tell that this part of the graph is really dense and this part is really sparse because there's too many dots behind each other. And so the first thing you might want to consider is, depending on the type of graph, using a bit of jitter so that it's just a little bit around. But in this case, because the numbers themselves are not quite like 100, 200, but they're like 18.4. It seemed fine to just have the numbers, but what I've done is I've used a bit of transparency. And so the transparency highlights that around here, there's lots of glyphs all kind of around overlapping. And over here, it's a little bit more sparse. So here we can have a look at the figure in Python. And so first I'll run this, and we got to import our mdates. And I won't detail all of it per se, except to just highlight the things that down here I've put in some parameters that I'm going to use for annotating. And those didn't come from the data originally. They came from other places. So for example, I looked at the mean for a pregnancy in terms of days. And then we have that after Christmas. And then we have the standard deviations as these ranges. And you can also just get a sense of some of the different details that we're putting in here, including, what day is going to be the minimum and how we're going to label that. You'll see here I've got plot.text. So recall that what we're doing is adding things to this plot. And right here we can add this v-span or v-line or even text itself with some coordinates. So what we did is I used the actual value itself to set the coordinates, and then we offset that value a little bit, so it's not like right on top of the point, but over to the line. That would be something that you would want to finish by hand yourself. You wouldn't necessarily want to automate that. What you would want is just to deliberately determine what you want to do in terms of telling the story. So uniform distributions are probably the most boring of distributions. They're just even. There's no real information in the distribution, but there's lots of other kinds of distributions. So really common ones would be a normal distribution, as mentioned earlier. It's where we would have some value, which would be the expected value, in the middle, and it would just become increasingly less likely to see values as we get away from that. And here we have another one. This is an exponential distribution. Now, online, you'll see a lot of examples of really skewed distributions like an exponential distribution. It seems that the number of people or the number of messages that people send to each other would follow an exponential distribution. There's some people with whom we would send a lot of messages, those we're very close to, and some for whom we might only talk a few times or maybe just once. And on the other hand, different things that we may measure would look more like this. Often things like opinions can be seen on a normal distribution, or sentiment, where there's kind of an average and things get decreasingly less likely away from it. Now, different processes can be used to create distributions that have similar shapes. So here we have an example of a Poisson distribution and an exponential distribution. They're calculated differently because they're based on different kinds of ways of drawing random numbers. But they both end up being pretty skewed. The important part for our purposes here is to think about whether the distribution has some sort of meaningful expected value, like a midpoint, like a mean, whether it has different sort of humps or lumps, which might imply different categories, or whether it's extremely skewed. So the other interesting thing to point out here is how we can have multiple plots in the same figure. So before we had figure and axis, and we were just sort of adding things to that AX. But in this case, we can have a figure which represents the overall image that we're trying to render, and then subplots. So not just AX, but now we have AX1, AX2, and AX3. As we can see here, this distributional plot, we're labeling this one with AX1. That's what its axis is, and then 2, and then 3. And these axes, we can then actually layer lots of plots down there, should you want to. It's not as common, but it is certainly common to show 2 or more plots side by side. So even though before I've said that generally in data science we're interested in distributions and the qualities of distributions, we tend to be interested in multiple distributions. And that's because it's not just the shape or size of one, but whether another can help us learn about the first one. And if it can, then we might say that there's a relationship between the two. Now, we don't know if that relationship is causal or not, but we do know that learning something about one distribution can help us learn something about the other. Now, distributions, how we consider them jointly really depends on some important qualitative differences in the distribution. So the key one is whether they're categorical or numeric. Is this something that you can order? Can you rank order? Can you go, along a line? And we might think, color, for example, kind of can be one or the other. We can think of colors as categories. We can have red and orange and green, or we can think of color as about the frequency on the electromagnetic spectrum, for which we get that wave of light. And so when you can see these bands of light, they're like actually continuous distributions about how fast this wave is vibrating. Or we can think of them categories as in qualitative colors. Now, that distinction helps us think, are we trying to split up a distribution so that we have the distribution for red or for orange or for green? Or are we trying to compare the order of the values, so as it gets more up or down the rainbow, I don't know, does it get more fashionable? I'm not really sure what we would correlate with color, but certainly a lot of other measurements we would want to correlate with each other. So in addition to whether the data we can think of is like categorical or continuous, whether it's discrete categories or something that we can order, we can also take an interest in the ordering itself. That distribution, is it really, really skewed, or is it more kind of like a normal distribution? And so, for example, in the case of Twitter data, we might think, let's have a look at two relationships. One is how often I would like someone's content and how many followers they have. Well, if I follow someone with like a lot of followers, millions of followers, this might be like a world leader or a celebrity or something, and I also follow some of my friends and maybe some journalists or something, what we'll have is a really skewed distribution of followers, with some people with millions and most people with few followers. So correlating that with how often I like their content probably wouldn't work very well, because the few people with like millions of followers might really stretch out that distribution. It would be overrepresented. We would say it has too much leverage. So what we can do instead is just rank order them. So we'll talk about who has the most followers, give them a value of 1, and who has the second most and give them a value of 2, and go down this. And then what we've done is we've kept the order so we can look at the relationships in order, but we haven't parameterized the measurement. We haven't said this measurement is so much bigger than another. We've just said it's the first, and this is the second largest, and the third largest, and so forth. And so in those cases, we can use non-parametric tests rather than parametric tests, which might more reasonably account for the skew in the data. Now, we might also want to consider whether the data represents counts or relative measurements, as counts are something where we can count an infinite number up, but for ordinal measurements, say if we have a strongly disagree scale to a strongly agree, it's a 5-point scale, then it's much more constrained. And so we can't meaningfully extrapolate from the trend line going up from strongly disagree to agree to some sort of like super agreeing or disagreeing. We might also want to think, is the data meaningfully divisible? I remember seeing a cartoon a long time ago with an average family sitting down watching television, and they had their 1.5 children. It was kind of a kid who was only half drawn, and the humor came from the fact that, well, some things are not divisible like that. So when we report on them, we might want to report on, say, the median number, or try to find the round number that's related to what we want to divide. On the other hand, with something like time, we might be able to talk about something being a couple nanoseconds in difference to something being a year, and still have lots of ways to divide within. Now, we might want to think, do the distributions that we're trying to correlate represent repeated measures or independent measures? So in that case, we can think of, are we looking at the change from one time to another? Or are we looking at two different populations and how likely they are to, say, respond to some stimuli? Now, these things matter for the display of a single distribution, but they're particularly important for joint distributions because they help us choose what kind of measurements we're going to see first and how that's going to help us build intuitions that we may want to test statistically or illustrate visually for the things that we think are important to test statistically. So as I said before, the reason why we look at two distributions is because we want to think of something as being able to help us inform the other. We know something about one, it'll help us know something about another. Now, the way we do that, if we have two continuous measures, we can use the product moment correlation, or just a correlation, and that's the parametric one. And then if the data is really highly skewed, or if it's ordinal, we often use Mann-Whitney-U, which is essentially the Pearson, but it'll have the rank order. It's often also called Spearman's, and we'll see it's called Spearman's in pandas or in Python. Now, when we have one continuous variable and one categorical, what we want to do is something like compare the mean value between them, and so that's what a t-test does, or an analysis of variance, which compares the mean across a number of groups. And then we have two categorical measures. We don't really order them per se, but we often use a chi-squared to say, if we have two measurements, people's whether they like the color red or the color blue more, and whether they are a morning person or an evening person, shouldn't really correlate. So we just assume that there's 4 boxes then, and all of our samples should show up in each of the boxes, proportionate to how many morning people there are and how many people who like red versus blue. Now, if we have that proportionate sense, and yet we still see many more people who like red in the morning group or the evening group, it's outside of our expectations. We covered that a little earlier, and that's how we use a chi-squared to compare those joint distributions. And we can see them visually as well. So this right here is a scatter plot, but also this is a nice one with some extra histograms on the side. And as you can see, these are two broadly normally distributed points right here. This is log normally distributed, so if we look at it on a log scale, it should look more like a bell curve. And this is just normally distributed. And so there really shouldn't be any relationship between the two. And you can see that it's hard to draw a trend line this way. It just seems like it would go straight through. Now here's what we would do with a categorical and a continuous. And so we have, these are 3 different measurements, or it's really the same measurement, but across 3 different species of flower. We'll see those flowers now and again in a bit. Now with 2 categorical variables, we don't really do much in terms of drawing the points, but what we can use bar charts for that, but we also use tables, and also later we'll see a heat map. Now you can use a third variable like that, and you can do that either with continuous data or with categorical data to help make things a little more visually interesting. Now here I'm showing a pair grid. Now I don't necessarily use pair grids a lot, but they're really information dense, and I like what this one can reveal about this particular data set. Now this is a data set of measurements of flowers that was collected an awful long time ago, I believe actually by Fisher, and it was one where we have 3 different species of flower, and they're all pretty similar looking, but they have some slightly different features. And we can see here that there does appear to be some relationships in the data, but those relationships are kind of flower specific. But if we look at these one right here, the versicolor and the virginica, those flowers actually, it looks like they're a little closer to each other than this setosa flower, which is, as a blob, kind of seems slightly distinct. So that's going to play a role later on. Now if we look down here at petal length, look at this this line right here. It does look like there's a pretty strong correlation between petal length and petal width for all of the flowers. It all seems to kind of go up in this nice trend line. And the same can be said right here. Petal length, petal width, and sepal length, sepal width. Sepals are the little green bits just below the flower. Now what we have here on the axes, or on the diagonals rather, is the single distribution for each of these values. So this is sepal length here and there, so that's what it looks like. And same for width, length, and petal width. And on the offsides, I have both a scatter plot and I have this is a kernel density estimate. So what this says is this is where we might see the most points. Now, as you see here, there's lots of points occluded if on this particular chart. So we could use transparencies, but the kernel density also shows us where it's the most dense, or where the dots are the most dense in the frame. Now, one thing here, look at sepal width and petal length, and we're going to look a little further in that because it can reveal something about data that we can use in a lot of other places. Now, what we have here is we can see sepal width and petal length. We can see that each one of them seems quite distinct. Now, if we were to draw a line down through here, then what would we get for our relationship between the two? It seems like because they're distinct, it's going to do some interesting things when we look at some correlations. So we'll see that in an elaboration model now in a second. Before we do that, I want to zip down to showing the iris data. So now the iris data is easily downloaded from with Seaborn, and I do so just a little bit right here because of the way the columns come down and play nicely, or don't play nicely with LaTeX. Now what we do here is first, and if you get an error here in an earlier version of this, because in an earlier version of Seaborn, it would just assume that that's X, but it doesn't anymore, so that's why we have X in there now. And hue again means species, so it gives a different plot for each one of them. Now it's a KDE plot in 2 dimensions, so what that means is wherever the distribution is the most dense along this, we're going to see it. So it's like a histogram, but as a kind of smoothed histogram. Now the pair grid, you'll see that here we are able to set a different plot type for the upper and the lower, as well as on the diagonal, which I think is pretty cool there. It's going to take a second to run. And yeah, here we have it. And also again, because it's SVG, it's nice and clear. If we zoom in, it re-renders it, so that way we can zoom in. Now, I said there was something kind of up right there, so let's have a look at that as a heat map. Now, we can see that heat map reveals that sepal width does appear to be a bit out of step with the rest of them there. And so What might be going on with that? Now, with the elaboration model, this is a way in which we can approach two variables with a third variable to help us clarify a relationship. So what happens when you account for a third variable? So if z, this third variable, correlates with both of the first two ones, and accounting for z eliminates the relationship between x and y, then the original relationship was spurious. We just happened to think that there was a relationship, but it might have been something else. In the prior chapter in the book, I give the example of like ethnicity and circus. It's kind of a facetious, fictitious example, but it does show what we might think of as a spurious relationship. Now, sometimes we see a different relationship where, when you take z into account, the original relationship wasn't significant, but could be, and we're going to show this in a bit. Now, if z doesn't alter the relationship, then we can think the relationship is replicated, and that's often what we do when we have some existing expected relationship between two variables, and then we say, well, we'll test it, but this time the relationship between, eating sugar and energy, we'll do it when the room is warmer, or we'll do it when people are doing a team building exercise rather than a math quiz or something. And if these things don't make a difference, then we could say the original relationship has been replicated. Now, here's one that's we sometimes see. If the relationship only holds for some classes of z but not others, then the relationship is considered a specification. And now there's a couple others, interpretation and distortion, but let's have a look at how that can help us kind of pick apart these sort of odd negative correlations right here. So what's happening in the pair plot, we see three flowers representing three different clusters, or distinct clusters. So now you'll notice if we do a correlation for all of our data, we can see here and .-43, so that's petal length and sepal width, and minus 0.43, and it's very significant. But what it's doing is it's going between all of these petal length, so it's going between all of these values, and it's drawing this line going down this way. But when we actually pick it apart, we see for setosa, this blue one, there's not really a lot of correlation between petal length and sepal width, and so it's not very significant. But for versicolor and virginica, the relationship is pretty clear, and you can see it's highly correlated and it's very significant. So which of these happened? We might think it's suppressed, but I actually think that this would be a consideration of a specification here. So the relationship got specified. But, it's kind of debatable. It's an interesting example because the relationship wasn't simply null. In this case, the relationship actually changed direction. And so that is kind of revealed. It was suppressed when we see that this one right here wasn't really much of anything, but their relationships now become more obvious. And finally, in the Jupyter Notebook, we can see those correlations down here, and there they are. There's some other stuff for us to have a look at, and that's covering in the book about t-tests and analysis of variance. But we don't really, we're not going to cover it too much here in the slides. The important thing for us to consider with this is that what we're looking at or looking for is the mean value for each of these distributions. Do they all overlap? And so a t-test would be if you only really have two distributions. Does their average value, does it overlap? Now we might say, what do you mean overlap? It's either the same mean value or it isn't. But the thing is that we have not just the mean, but also the standard deviation. So if that standard deviation overlaps, if those confidence intervals overlap, then even though the mean might not be exactly the same, we should be able to suggest that it's close enough to being the same that there's no real difference, or that those means are far enough. They're outside of each other's confidence intervals, so there is definitely a difference between the two. So now here with the analysis of variance, what I've done is put together a box plot, and so we can see is there a significant difference in the sepal width, the little green part in the width of that across these flowers. And there certainly might be. We might suggest it because here is the midpoint line in a box plot for each of them. And so given the range of variables, it might be the case that setosa and versicolor actually are significantly different in the average sepal width. So here's how we might do this in an ANOVA. It's called a one-way ANOVA, so we're going to go by one set of groups. And what we've done is shown that indeed the p-value, because it says e minus 17, is really, really low. That suggests that there's definitely some difference within this distribution or within these groups. Now, the important thing to note about this one way is it doesn't tell us which groups are different. So it can't, by itself, just tell us that it's setosa versus virginica, setosa versus versicolor, or setosa versus either of them. Now, I mean, the smart money is on, it's definitely that one, that those means are definitely different enough that they have different sepal widths. But what about virginica? We're not sure. And so for that, you would do post hoc tests on a one-way analysis. So now to summarize the chapter and some of the ways in which we've looked at both visualizations and statistics together. Expectations and observation should work together to help create insight. Now those expectations, we often think of them coming from the literature or academic work or from our own lived experience. But those expectations, when we want to test against them, we want to be a bit more formal about that. We want to say, should the expectation be some specific average value? Should it be a specific distribution, a shape or a trend? Should we expect outliers? And then we go out and have a look at data and then kind of bring that back to our expectations. And we can do that in a tabular format, in a statistical format, or in a visual format, like some sort of graphical one. Now, they have different goals. Visualizations can help give us intuition, such as why there might be a kind of a bump in some sort of trend when it should be uniform, whether there might be an outlier that's kind of has a bunch of leverage, whether the distributions really represent different distinct subclasses in the case of those flowers. Now, that gives us an intuition, but then we would want to turn to statistics and statistical approaches often to help us determine whether that shape, whether the differences between these, whether they've occurred by chance, or how likely is it that they've occurred by chance, or whether it's not by chance, it's because there's some meaningful difference. So we might say a statistically significant difference between one distribution and another. Now we can test for whether a distribution is different from what we would expect using a chi-square, but it doesn't tell us much about, there's no sense of a trend within there. So with those digits from 0 to 15, or the first 16 digits, a chi-square can tell us that there is definitely an outlier, or there are definitely points that are pretty far away from our expected value. But it's not going to tell us if there's a trend, if that's because those points are larger or smaller. Now, on the other hand, a regression or a correlation can help us do that. It can give us a sense of direction. That is that trend line going up, or is the trend line going down? And then, of course, further, we could think about significance within that. So is that trend line going up and we're really sure it generally goes up? Or is it going down and we're really sure it's generally going down? Now, we can, not just a correlation, not just that single trend line through a distribution, but we can look at other ways of comparing joint distributions to see, is one going to help us learn about the other. Once we have two or more variables, we'll see a relationship, but that doesn't mean that relationship is necessary. That doesn't mean that relationship is causal. Now, to explore it in a causal manner is generally pretty complicated. It might involve certain differences in research design or different expectations in data. But we can use a third variable to determine whether that relationship that we originally saw can be replicated in the presence of this third variable, or whether that third variable kind of recovers a bunch of the information. It makes more sense than the original relationship or other kind of flavors of that, like the suppression relationship that we saw with flowers, where the correlation seemed like it was negative, but that's actually because we had three different classes, or really more like two. One with the blue dots representing setosa, which is its own kind of type of flower shape, and then the other two flowers, the versicolor and the virginica, which really did see a correlation within these values. Now, there's lots of ways that we can extend this sort of work. This is really just getting started at the baseline, but here's a couple practical things for you to explore. The first one is that sometimes our distributions are really skewed, and so they might look better on a logarithmic axis than on a linear axis. So explore some of those random number generators, and then within your visualizations, set the axis to be a log scale rather than a linear scale. Now, you can take one of the distributions or a couple distributions from some of the earlier chapters. In chapters 6 and 7, we were able to show some data from Reddit or Twitter, and perhaps we could have a look at how we can go back, make the aesthetics of those distributions a little more useful, a little more clear, now that we've seen all the different ways in which you can, add lines or shading, annotate a figure, and set the axes to them. And, there's so many different ways in which we can build models that this sort of topic will keep on going in its complexity and sophistication. But at the base of it is really a practice of taking expectations, examining them in relationship to observations, and then seeing whether we need to update our expectations as a consequence of that, and how confident are we in those observations as meeting those tests. And that confidence can come from showing the distribution visually, as well as to testing it statistically, and indeed using other approaches like the tabular presentation of data. So that's it. Thank you for listening this far. And up next is chapter 10 on cleaning data.